So you should have your notes out in front of you. We're going to talk about electrochemistry. During a redox reaction, electrons pass from one substance to another. The flow of electrons is called electric current. Cannot be harnessed to do work. Electrochemistry is the branch of chemistry can be harnessed to do work. We want electrical current. That's why we plug things in. That's why there's batteries. Electrical current does work. Electrochemistry is the branch of chemistry that deals with the conversion between chemical and electrical energy. There are two major branches of electrochemistry. The first is called electrochemical cells. The energy released by a spontaneous, so happens on its own, it doesn't need energy, chemical reaction is converted to electrical energy. So what we've done is we have gone from chemical to electrical energy. So one example would be batteries. Electrolytic, on the other hand, the other type of electrochemistry, is where we go from electric energy is used to cause a non-spontaneous chemical reaction. Let's spell that correctly or do the short form. Okay, so electrolytic, we go from electric to chemical. Electricity is used to make a chemical reaction happen. So some of the ways we do this is recharging batteries and electroplating. So first we're going to talk about the electrochemical cell. So chemical to electrical. The basic unit of all batteries is something called a chemical or electrochemical cell. Also, we can see voltaic cell or galvanic cell. Those are other words for electrochemical cell. It converts the energy of a spontaneous redox, so reduction and oxidation reaction, into electricity. This will be accomplished as the electrons are released from the oxidation half reaction and passed to the reduction reaction, which will absorb the electrons. So remember before we're learning about who's losing, who's gaining. Now we're going to harness that. Okay, so an example would be that we're going to use is this electrochemical or this redox reaction. Solid zinc plus copper in a solution goes to zinc ions to solid copper. Okay, there's two half reactions that are happening. First of all, we have zinc, and it's going to zinc. And what happens is we have how many electrons? We went from an oxidation number of 0 to +2. So we lost 2 electrons. Leo the lion says Gur, loss of electrons is oxidation. Okay, the other half reaction we have happening here is copper. We have copper in solution plus 2 electrons. We add electrons to it and we make solid copper. Okay, this was a gain of electrons, so this is reduction. Leo the lion says Gur. In order for electrical work to be done, we have to have the electrons travel through an external circuit. If we simply place a piece of zinc in a solution containing copper, a reaction would occur, but electricity is not created. So we make something called an electrochemical cell. We begin by getting 2 beakers and place metal strips in electrolytic solutions. In one, place a strip of zinc and ZNO3 in the zinc is in the zinc nitrate solution. And the other, we place a strip of copper in a copper nitrate solution. Each beaker represents one of the two half cells, but still there's no way for the electrons to move from one beaker to another. So that's what we have here. We have zinc in a solution, and we have a solid piece of copper. This is a solid piece of copper in a copper solution. Okay. Then what happens? The two half cells need to be connected in two ways. First, we need the electrodes connected with a wire. This is the external circuit, and what we do is we put a voltmeter to detect the electrical current. You can also see sometimes they put a bulb here instead. The bulb turns on to show that there is current going through. Second, we add a salt bridge. A salt bridge is a U-shaped tube that contains an electrolytic solution. In this case, we're going to use KNO3. We use KNO3 because it is an electrolytic solution. It also is very soluble. Okay, it allows ions to flow between the two beakers. This is the internal. So we have something called this salt bridge right here, and it has a solution. It's kind of plugged up on the ends, so the solution stays in, but there are things that can come down through it. Okay, the zinc half cell, so zinc over here, this one right over here, undergoes oxidation. Here, the solid zinc electrode disintegrates. So you can imagine this stick is slowly disintegrating. It's giving off little zincs. Zinc ions releasing electrons. We know it's releasing electrons because of its half reaction we saw over here. Zinc releases electrons. Okay, every time we go from that solid zinc bar into the ions, we release 2 electrons. Okay? By definition, the half reaction that undergoes oxidation is called the anode. So this is something new we're learning. The half reaction that undergoes oxidation is called the anode. That's the fancy chemistry word we use to describe that. And we have a new way of remembering it, and that is anox. The anode is a source of the electrons, making it a negative post of the electrochemical cell. So we're going to remember this by being anox. The anode is where oxidation occurs. Okay, the copper undergoes reduction. We saw that in the half reaction for copper. Copper is being reduced. We're gaining electrons. Okay, this is called, copper from the solution become deposited onto the copper electrode, forming more solid copper. Electrons are required for this to occur. By definition, we call this cathode. Okay, so the cathode, the way we remember that is reduction happens at the cathode. That's a red cat, and it is positive. So I like red cats, they're positive. Anox is negative. I don't know, maybe that ox looks a little sadder. So now we have copper. We have a whole bunch coming out of solution, and it's forming copper on here. Okay, it's forming solid copper. It is important to understand the roles of both the external and the salt bridge. So the external is where the electrical work is done as electrons travel from one half cell to the other. The electrons are produced at the anode. Electrons produced at the anode and where oxidation occurs. The electrons then travel through the wire of the external circuit to the copper cathode. The electrons are available for the copper ions and solid copper is produced. Then we have the internal circuit. At the anode, zinc ions are being produced and go into solution. So you can imagine there's all this zinc going in. So all these positive ions, a whole much of positive. This is too much positive in the solution. If this electrical imbalance is not corrected, the reaction can't continue. The excessive positive charge attracts the negative charge, the NO3 ions, or the anions, from the salt bridge, therefore keeping the solution neutral. So from this salt bridge, the NO3 comes out. Because remember, we have KNO3 solution. So we get a whole bunch of those negative NO3s come out to balance the too much positive zinc. Okay, so guess where the name anode and anion came from. They're kind of the same idea. So anions are happening at the anode. We have anions coming. Okay. At the cathode, oh, so anion, if you didn't know, was just a negative ion. And then a cation um, is a positive ion. Anion, cation. Hopefully those are review. Okay, at the cathode, the opposite occurs as there's more Cu coming out of solution. So as that Cu is being deposited here, we get rid of all the positives. We need more positives to come down. So that's why the copper comes, or the potassium comes down. So a couple things we need to write down. At the external circuit, we have electrons flow from anode to cathode. Okay. The internal circuit, we have anions, negative ions go to the anode. And the internal circuit, that salt bridge, we have cations to cathode. Okay, so this is your little summary table, kind of your major key point we're getting from here. It is very important to note and remember that unless electrons can pass from one electrode to the other, the reaction will not proceed. Okay, I have a video right now. I'm going to stop this recording. You need to watch the video directly underneath this, and then we'll continue with the notes afterwards.